All right, so in this screencast, we're looking at an example where there's going to be 3 links. I've got them sort of drawn out in red, blue, and green to begin with. And so this conversation that we've been having here in class, we've been talking about, well, like, what's the innermost function? And we want to consider, okay, what's being done to start with? Well, we're raising something to the 4th power. Okay, what is that something that we're raising to the 4th power? I'm going to say let u equal the thing that's being raised to the 4th power, which is cosine of 7x squared plus 1. Okay, and we'll start there. So what I can do is I can rewrite, as I oftentimes do, instead of looking at this as k of x, we're just going to look at this as y equals. All right, so what I'm doing is I'm rewriting, instead of y in terms of x, I'm going to write this as y in terms of u. Okay, so in other words, y equals u to the 4th. Okay, now earlier when we were discussing this problem, we said, hey, what's the derivative of u to the 4th? And you guys would all say what? Good. So that's dy du. And that's the first link of this chain, which is going to be 4u cubed. All right, so I'm going to stop there just for a moment. Make sure everybody's caught up. What we did was we said, hey, what's being raised to the 4th power? And let's substitute in place of that so that we've got now, instead of cosine to the 4th, we've got u to the 4th. Because u to the 4th is easier to differentiate. Very easy. We just found it for u to the 3rd. So I'm going to stop there. I won't back substitute until the end. The second step would be to say, okay, where's my black pen at? There we go. All right, second thing would be to say, okay, well, what is the derivative of u with respect to x? Well, I don't know that just yet. I'm trying to differentiate cosine, but there's a function inside of that cosine. So let's make a second substitution. So I'm going to say let v equals 7x squared plus 1. So that instead of differentiating u with respect to x, I can very much easily differentiate u with respect to v, right? Because if we're subbing in place of 7x squared plus 1, the letter v, then this just becomes what's the derivative of the cosine of v. Do y'all remember your derivative rule for cosine? Good. So now du, instead of du dx, is du dv. That's just going to be negative sine of v, and we've got our second link in the chain. We've got du dv. Question, Connor.
So how did you go from cosine 7x squared plus 1 to cosine? Oh, is that? Never mind, that's v.
So what we're doing, and that's a good question. What we're doing is over and over and over again, we're looking for a way to simplify the matter out. If I had told you today, hey, what's the derivative of the cosine of 7x squared plus 1? You say, well, that's a little bit too complicated. If I had said, hey, what's the derivative of cosine of v? Everybody's on board with that. You say, I know the derivative of cosine of v. It's just negative sine of v. Okay? So what we're doing is we're making use of substitutions. Now, our last thing to do will be to find what's the derivative over there, this third link in green, what's the derivative of v with respect to x? So if we come over here and we say, what's the derivative of v with respect to x? I've got v defined already as 7x squared plus 1. So what's the derivative of 7x squared plus 1?
It's 14x.
14x, that's what we saw earlier. Matthew, you look like you have a question.
Yeah. I'm curious, what happened to our 4u to the 3rd? Where does that come from?
All right, so look at what we're originally trying to find. We're originally trying to find dy dx, okay? And so what that's going to do now is that's going to require us to multiply those 3 links of the chain. So here's the first link, dy du. Here's the second link, du dv. And here's the third link, dv dx. And think about that dimensional analysis we mentioned yesterday from chemistry. Like, what happens, let me zoom in here, what happens when we start multiplying these 3 fractions? Well, the du's would cancel out, the dv's would cancel out, and we'd be left with dy over dx. Okay? So when we take these three lengths, we want to multiply the three of them together. 4u cubed, negative sine v, and 14x. We're going to multiply all three of those together down here, and I'll do that in orange. So we got 4u cubed times negative sine of v times 14x. Okay? Now, the answer that we're looking for is supposed to be with respect to x, or we're differentiating in terms of x. Okay? So I'm good with the 14x because that obviously has x in it. What about sine of v, or negative sine of v? Could you rewrite negative sine of v in terms of x, knowing that v equals 7x squared plus 1? Substitute back in place of v. What are you going to get there? Negative sine of 7x squared plus 1. Good. So we got two of these guys now in terms of x. Now we just need to worry about this last one. 4u cubed. What's u the same thing as? Cosine of 7x squared plus 1. And so now we got all three of those in terms of x being multiplied together. Aaron.
I get where we had you were getting the 4u third minus that point at the top. And then when you start substituting, you substitute like the original function back in for the variable that you let it.
Absolutely. Yes.
That's the back substitution.
Yes. So what we're doing down here in orange is the back substitution. We're saying, hey, I can't leave this u in my answer. I need to replace it with what u stood for. And if you're diligent in writing the problem out, and if you go to the trouble of saying, hey, let u equal this, then like what I've got underlined here in this wavy line, u is directly substituted back into place. Here's this expression for u that I can just plug in place and get everything back in terms of the variable that we're supposed to have it back in terms of.
So, in the end, you're just taking the derivative of your outside function, multiplying it by the two inside functions, derivative of the second to most inside function, multiplying it by the inside function, and then the derivative of the inside function.
Yeah, I'd change one way that you said it. Instead of multiplying it times the inside function, you're going to say evaluated for the inside function. So it's like you're taking the, quote, inside function, you're plugging it back in. Temporarily, just pause that for a second. Go back with me to this very first example that we did, right? This very first example that we looked at yesterday, we said, hey, look, you're going to differentiate the outer function. So we took our 4, we pulled it down front, and we dropped it by 1. Right? So that's where our 4u cubed came into play. And then we said we're going to evaluate in place of that u, instead of 4u cubed, it was 4 and then that expression cubed. That's that back substitution that Aaron was just asking about a moment ago too. And then we follow that up by multiplying it times the derivative of the inside function. With this new example for today, we're just doing that a couple of times over. We're doing it once in terms of u, and then again in terms of v. And we need to clean our answer up, and I'm kind of thinking that some of y'all might have already done this. We've got a 4, we've got a negative sign, and we've got a 14. Let's put all that together. 4 times 14, would that be 56? So we're going to have a negative 56. So I got my 4 out of the way, I got my negative out of the way, and my 14 out of the way. Let's put an x there. Let's do cosine cubed, 7x squared plus 1. And then let's do sine 7x squared plus 1. And that would be the most succinct way of writing up our answer for the derivative there of that function. That's not an easy problem. I mean, I saved that one to the end because that's the, if you've got 3 links, that's the most complicated one. And truth be told, this is not an honors calculus class, so I'm not going to slam you guys with a bunch of triple chain rule problems. Last year's group struggled with it, and I recognize that fact. But I want you to have seen it so that you understand at least, how it works when there's a function within a function within a function. Van.
So you know how yesterday you did the thing on the sideboard with the just drop it,
and keep the original and then find can you do that with one of these?
So yeah, absolutely. So the question was, can you work this one out without making it without showing all of like the background steps, in other words. And yeah, I think absolutely we could do that. Now that you've seen the process and at least we've got our answer, I'll show you how that would look. If one were to do it like in real time, let's say. All right, so K prime here would equal. All right, so I recognize the outer function is something raised to the fourth power. So I'm going to say 4 times that something raised to the third power. Now what that something is a function, cosine 7x squared plus 1. All right, and since that's a function of x, I need to multiply by the derivative of it. Okay, the derivative of it being, okay, so cosine, I know the derivative of cosine is negative sine of 7x squared plus 1. And then I recognize, well, hey, look, that's an inside function as well. So I need to multiply by the derivative of it. And then I go over here, I say, all right, well, what's the derivative of it? All right, that's going to be 14x. And so now I've differentiated my 3 times. I've differentiated the outermost. You say that's so much easier?
Yes.
I agree.
Yeah.
I agree. All right, so that's the outermost. This is the middle one. And then this is the innermost. And you keep differentiating until you have got it down to where it's in terms of no other function. Like what I mean by that is 14x, I can't differentiate that anymore to make it any simpler. There's no, it wasn't like, x was really something else in disguise. It's just plain old x. So you take it down to that point. And then, of course, you would simplify out your answer and get like what we got there in orange.
Wait, okay. So if you had like 5x cubed, and then
so let me pause you real quick. So like we could make this, at the risk of overcomplicating things, we could make this like if I made the square root of or the cube root of, let's just do cube root of x. Okay, so like if this was instead of x squared, if this was the cube root of x, let's just pretend like that's what it was that was being squared, and then you got 7, and then you got plus 1. Something like that, okay? Then this would be, all of these would be cube root of x, and we would need to take that into account, and then here at the end, you would need to go one step further times the derivative of what that cube root of x would be. So you would keep going until you got it down to just plain old x. Okay. Hey, let me get you guys to try one from the homework, okay? And then I believe that I'll call this screencast. I'll call it quits on this screencast. Let's see if I can find a triple. Yeah, I think I like number 236. So let's do 236 on your own. If you are watching at home, go ahead and pause the video, and then we'll pick the screencast back up once everybody's had a chance to work. Number 236. All right, so here this problem goes. First thing I'm going to do is I'm going to recognize 6 plus secant pi x squared as u. I'm going to say u equals that. From our step-by-step process yesterday, that was step number 1, right? Now step number 2 is going to be to differentiate that. So let's find du dx. Well, I come over here and 6 is easy. What's the derivative of 6? 0. But the derivative of secant pi x squared is tough because pi x squared in and of itself is another function, right, on the inside. So what I need to do is I need to say, well, scrap that, and instead of finding du dx, let v equal pi x squared, and I can try and find du in terms of the derivative of u in terms of v. So u now equals 6 plus the secant of v, which now we're saying, I could definitely find du dv in that case. Okay? And we could definitely find the dv dx. dv dx. All right? Which one do we want to find first? dv dx or dv du? Du dv. You want to find the one in blue, du dv? All right, so we already said the derivative of 6 is 0. What's the derivative of secant? Look at the top. Secant v times tangent v. And we'll do our little back substitute in a minute. Okay. In red, what's the derivative of this one? Remember, pi is just a constant, by the way. What's dv dx in red? 2 pi x. Okay. So with that, we like dv dx because now it's in terms of x. Let's go ahead and back substitute in blue. What was v the same thing as? Instead of secant v, it's secant. Look for what v is. Pi x squared. So secant pi x squared, tangent pi x squared. Same thing. Now what I haven't done is I haven't rewritten in black what y is. Y is now the same thing as the square root of what? I've got it boxed. We said u equals that. So this is the square root of u. Does anybody have their square root rule memorized? If I ask you what's dy, du, do you know that the square root of u's derivative rule is? It's 1 over 2 square root of u. That's a derivative rule that we've used power rule before. Like I got space down here to rewrite this. You could say y equals u to the 1/2. You could pull that 1/2 down front. Pull that 1/2 down front. And hold on one sec. You would pull that 1/2 down front and dy du would be 1/2 u to the negative 1/2, which is the same thing as 1 over 2 u to the 1/2, which is the same thing as that. I would just memorize this if I was you guys. Memorize the square root rule. All right, so what we've got now is we've got all three links of the chain. We've got dy du, du dv, and dv dx. So if we put that together, if we're looking for dy dx, that's going to be dy du times du dv times dv dx. And we just want to plug in all three of those links that we've got, and we'll be good. 1 over 2 square root of 6 plus secant pi x squared. Du dv is secant pi x squared tangent pi x squared. And then, what's dv dx? That was our easiest one to find. Yeah, that's in red, 2 pi x. So we just multiply the three of those together, and we get a big fat fraction, as I was mentioning earlier. 2 pi x secant pi x squared, tangent pi x squared, all over 2 square root of 6 plus secant pi x squared. What simplifies out there? Yeah, we can take the 2's out. And we wind up with our answer of dy dx. That is not an easy problem. That's probably more of an honors level problem. I don't want you guys stressing about having to know how to do one of those. I just wanted you to go through the process of seeing one. Okay? And again, it's just a matter of saying, okay, well, let u be this, and figure out what u is and how to differentiate. And then if you, in that process, have to differentiate, again, let v be that. It's just, again, a chain within a chain. Davis, you had a hand up.
Yeah, is there a simple way, like, can you get the same answer if you just multiply the derivative of the first function and the second and the third child?
Yeah, so in essence, Davis's question has gotten to the point, again, that Eli had brought up, like I hate to call it shortcut, but like the shortcut way of thinking about it is, hey, can I simply multiply the derivative of the outer function times the derivative of the middle function times the derivative of the inner function? Absolutely, that's what we're doing. Again, this was the derivative of the outer, derivative of the middle, if you will, and then the derivative of the inner. The whole thing hinges upon, however, your ability to go and back substitute such that everything is in terms of x. Okay? So those three spots that I've highlighted there, initially they weren't. Initially they were, where we had a u in it, where we had a v in it, and then the last bit still had an x in it. We were okay on that. But you just want to make sure you go and back substitute where I've got highlighted the u's and the v's, and that way we make sure our answer is all in terms of x. Thank you very much, Mr. Springer. All right, for this screencast, I'm going to call it quits, and then we're going to look at some more examples from the homework that are not so arduous in nature.